So, as material science students, we've been using microscope to identify material characteristic and grid structure. But are you aware of the color codes on each of the objective lenses? An international color code has been devised to make it easy to identify the magnification of an objective lens. There are a lot of objective lens color here, but we will be focusing on only the four main colors that is frequently used in a microscope. The code is red, yellow, blue, and white. So the three types of objective lenses that you need to know is based on their magnification power. So this includes low magnification objective, medium magnification objective, and high magnification objective. In special condition for a high power objective lenses, which is 100, oil immersion need to be done. So why? Immersion oil increases the resolving power of the microscope by replacing the air gap between the immersion objective lenses and the cover glass with a high refractive index medium, and it reduces the light refraction. So to figure out the total magnification of an image that you are viewing through the microscope is really quite simple. To get the total magnification, take the power of the objective and multiply by the power of the eyepiece. So in other words, if a 40 magnification power objective lens is used, the total magnification would be the power of the ocular lens, which is 10, usually 10, multiplied by the power of the objective lens, which is 40, and it will result in 400 times magnification power. So many times, microscope objective with high magnification power will have a very short working distance to the focus spot. Because of this short distance, if one is not careful while focusing on the targeted specimen, the end of the microscope objective may crash into the object under study. Immersion objectives also, which operate with a liquid medium of defined refractive index, which is oil, between the front lens and the cover slip, are more restricted in working distance lengths. If the working distance is too large, maintaining a distance of the oil between the objective front lens and the specimen can be a problem, and it could lead to aberrations and could possibly destroy the image resolution. So by that, we use long working distance objectives that are really ideal to use when the application requires a significant distance between the objective lens and the object. For many applications, a long working distance is highly desirable, and long working distance objectives are particularly very useful when examining specimens through thick glass walls for chemicals and metallurgical microscopy, where the objective front lens must be protected against environmental hazards such as heat, vapors, and volatile chemicals by a thick cover slip. And most modern bright field microscopes are parfocal. But what does it mean by parfocal? It is the ability of a microscope to stay in focus as the user switches among the objective. In a good parfocal microscope, less than 1/8 of a turn of the fine adjust should bring the image back into focus. It is very helpful for a microscope to be parfocal because the user does not have to adjust the focus knob when changing the power of magnification. So for example, when a person viewing a specimen under a high magnification, the person can then change to a lower magnification and the specimen should still be in focus without the person having to manually adjust the focus. Therefore, parfocal microscopes are easier for beginners to use.